Hello, today I'm going to talk about two different definitions for Southern Ocean front. If we look at this image from NASA, you can see the really nice structure of the ocean. The lines correspond to the currents, and the colours on those lines are the temperature of the surface. You can see that there's a lot of structure, and hopefully we can use machine learning algorithms to pick this apart. If we look at Chris Chapman's work from the last few years, in particular his Nature climate change paper from earlier this year, he's been challenging the traditional view of fronts. And this figure from his paper nicely summarizes this view. So the lines in this image are the isopycnals, and obviously at the front themselves, they steeply tilt. And this corresponds to a pressure gradient, which is balanced by the Coriolis force created by the jet that runs along the front. And this is one way of viewing the front itself as some sort of sharp gradient in the ocean properties. But the other way of potentially looking at it is if you look on one side of the front, we've got a very different vertical structure from on the other side of the front. To look at this difference between these two different views of fronts more carefully, then we can look at Chris Chapman's paper and see that he defines the global and the local definitions of fronts, and these are two example images of that. So what we've got is various methods such as the contour method, the water mass criteria, and I'm introducing Gaussian Mixture Modeling, which are all global methods because they allow the algorithm that we're using to have all of the data from all over the ocean to define where those boundaries between different fronts should be. The advantage of this method is that it's highly interpretable, and it's useful for oceanographers to be able to talk about the polar front or the sub-Antarctic front. But the takeaway from this is that it's very hard to define where those fronts should be or how many fronts there should be. If we look at a local method, such as this sea surface height gradient, it's very, with some sort of threshold, it's very clear that the fronts are much less interpretable and form this sort of spotty pattern, and there's no unique number of fronts around the ocean. Those don't necessarily join up, and those will vary over time. So there are a number of techniques such as gradient thresholding or Sobel edge detection or skewness, and it's easy to define because there's only one threshold you need to pick, but it's hard to interpret. The data I'm using is BSOC I106, which is a nice state estimate product from Verde and Maslov 2017. I've got the velocity field here, which nicely picks out the structure of the Antarctic circumpolar current. The data I'm using is monthly mean temperature and salinity profiles between 300 meters and 2000 meters of depth. The 300 meters is very similar to Isabella Rosso's work from earlier this year, and that's to cut out the top 300 meters, which potentially will be heated and cooled during the seasonal cycles and therefore might make the boundaries move about. The preprocessing step that we chose to use was from Essian's paper from 2017, where essentially we put the temperature and salinity profiles together, rescale them, and then we do principal component analysis, choosing the first three principal components based on the North criterion. You can see that the first principal component is essentially a simple south to north, cold to hot transition, and the others are more complicated. We fit the principal components once for the whole dataset alongside the Gaussian mixed models that I'll come to next. For the global method, we use Gaussian mixed modeling in a similar way to Mazzet's paper from 2017 or Dan Jones's paper from last year, where essentially you've got K clusters, or in 3D, K ellipsoids that move about to maximize the expectation of the data. This is really useful because it gives us the posterior probability of any point being part of any cluster, with the caveat that it has to be part of one of the clusters in the model. We define, thanks to Anita Thal, the I metric, or the interclass metric, where we look at the probability that a point is part of its most likely cluster versus the runner-up. And if those two probabilities were equal, we are maximally uncertain, and the interclass metric is 1. And if the probability that it's part of its most likely cluster is 1, and we're maximally certain, the I metric is 0. So this can be thought of as the probability that you are in the interclass region. If we look at this in 2D space, then we can see the clusters being sort of hard labeled on the left-hand side, and you can see that there are 5 clusters in this example. On the right-hand side, you can see the Gaussians, the clusters that this corresponds to. underneath the data and the I-metric overlaid on top on the points that it applies to. And so what you can see here is that the I-metric clearly highlights the boundaries between those clusters, but I should talk about the caveat of, if you look at the left-hand side, there's an orange spoke coming off from coming down there from using cluster 3, and that might be surprising to you because it looks like it's much closer to the Gaussian of cluster 2, but this is because the cluster underneath the Gaussian underneath the second cluster is very thin, and therefore the spoke is many more standard deviations from cluster 2 than it is from cluster 3, which is why the algorithm has to be much more certain that it's part of cluster 3 and sort of have this spurious certainty. If we had a much more complicated statistical model and added a lot more Gaussians, eventually the spoke would have its own Gaussian. But we had to make a trade-off between the simplicity of the model and its accuracy at describing every point. This trade-off can be summarized by the Bayesian information criterion, but unfortunately, the Bayesian information criterion for this particular dataset never plateaus, so we never get a minimum that we could choose an objective number of clusters, and this is a common problem in oceanography because the data is very continuous. If we look at a particular example on the ocean, we can see that this helps to highlight some very sharp fronts that look very similar at first glance to the classical definitions of fronts. We could say that the yellow one looks very similar to the sub-Antarctic front, the brown one looks very similar to the polar front, and the blue one looks very similar on first glance to the southern ACC front. Potentially more interestingly, if we just look at the I-metric as a scalar value over the ocean, you can see that at some points it highlights very sharp transition regions, such as north of the Drake Passage, or regions of very high complexity, such as by Kerguelen. But then if you look at a longer term mean, such as on the right, then you can see that there are some regions where, because of the high variability in where the fronts go and where the currents go, this means that this is largely smeared out, whereas in some regions where the fronts and the currents are very topographically constrained, such as upstream of the Drake Passage, the fronts are not smeared out over time. The local alternative using the same data is to use Sobel edge detection, as in Hjelmervik and Hjelmervik last year, where they just apply Sobel edge detection to the principal component fields themselves. In this particular example, we're just taking the Y-Sobel edge detection operator on the ocean to highlight this. So if we look at this in the first three principal components, you can see that the first principal component in particular looks very similar to the velocity field. And so this helps to highlight the fact that we can sort of look at fronts also locally as that which corresponds to the jets because of the pressure gradient force and the Coriolis force having to balance. In conclusion, what we've brought you is a new definition for what a front could be, based on water mass criterion in a probabilistic manner. This expands on the classical time average view of fronts and water mass boundaries. The paper and the GitHub repository for this work is in preparation, but we hope that you could explore this on your own datasets.